Alright gang, today we're looking at quantum numbers, which is just a way to talk about the location of an electron. So before we get into the numbers themselves, let's set kind of big picture what we're looking at. I want you to imagine we've got some atom, and here is its nucleus, and then we've got these different energy levels, like in the Bohr model, where the electrons can be outside of the atom. Now, we've been thinking of these, particularly in use of the Bohr model, as just being like this one area, just like a circle where the electrons can be. But according to the quantum mechanical model, it's more complicated than that. So I'm going to let's take this third energy level and let's zoom in on it, and let's make it really big so that we can see what's going on there. So in this third energy level, which we were thinking of as just a circle, but now we have to think of it as having some thickness. There's stuff going on in there. So this is zoomed in, and this would be inside that third energy level. It turns out that there are different places inside this that we call sublevels that have different amounts of energy. And one way to think about these sublevels having different amounts of energy is that some are closer to the nucleus than others. So I could divide this into three parts, really. And so each different part has a different name. We call the one closest the S sublevel. The next closest is called P, and then the next closest is called D. And all of these are in the third energy level, so we would refer to this as 3S, 3P, and 3D. So that's just saying that we can divide this energy level up into different areas, depending on whether they're closer or farther away from the nucleus, and we call those sublevels. And then to make it even more complicated, each one of these sublevels has particular spaces inside it where you're likely to find an electron, what we call orbitals. For instance, the 3s sublevel is just one giant orbital, so there's a possibility of finding an electron anywhere in there. For the 3p sublevel, there are three orbitals, so there are three locations to find an electron. So let's say there's one of them, and then there'd be another one further along the atom over here, and then another one over here. And then with 3D, there's 5 different places. So we'd have 5 of those scattered out around the atom. And each one of those is called an orbital, and an orbital can hold 2 electrons. So that was a lot of stuff I just dropped on you there. But the whole idea is that these rings, if you will, they're not actually rings, they're not really rings around it, but they're locations around there. These energy levels are more complicated. There's stuff going on inside these energy levels. And the quantum numbers are basically just a way to give a street address for an electron, if you will. So let's go through and let's talk about what each one of these quantum numbers mean. We'll start with N, which is what we call the principal energy level. So the principal energy level is just which one of these energy levels is the electron in. So if you want to think of this as an address, for instance, the address for the school is 150 Main Street, Maynardville, Tennessee. This N is sort of like the Tennessee part of that. It gives you a certain idea of where this is, but there's still a lot of space in there it could be. So N is the principal energy level, and that just tells you which one of these it's in. It's a very broad description of where the electron's at. And the way these are numbered is that the energy level closest to the nucleus is called the first energy level. And then the next closest is called the second, and then the next closest is called the third. So these are numbered 1 through, well, it goes all the way up to 7. So these can take, or this number can take a value anywhere between 1 and 7, 1 being the energy level closest, 7 being farthest away. You can potentially have more than 7 energy levels, but for our purposes, we're not really going to deal with anything past that. All right, now let's look at the next one, which sadly is not so simple to understand. It's represented by a script L, so think like a cursive L. And this represents the sublevel. Now remember, these sublevels are like locations within the energy level itself, and for each sublevel it basically represents a different energy, different distance from the nucleus, with S being the closest, and then so on and so forth. But again, this gets complicated, so hang with me. We have 4 different sublevels we can talk about: S, P, D, and F. And what I'm going to do is I'm going to make sort of a table out of this so we can get all our information about these sublevels in one place. All right, so first, before we do anything else, the number for the sublevels can have any value between 0 and 3. Again, we can get higher than that, but we're not going to deal with that much at all. And so each one of these, S, P, D, and F, gets its own number. And so that's the first thing we'll look at that. And the number for S is 0, 1, 2, and 3 respectively. So S is the lowest energy one, and it gets the lowest number, 0, 1, 2, 3, so on and so forth. Now the nice thing about this is that this can simplify a very complicated problem for us, in that not all energy levels have all the sublevels. So the way it works is that all the sublevels are present as long as the number for the sublevel is less than the number for the principal energy level. So for instance, the first energy level, n equals 1, there's only one of these numbers that's less than 1. So in the first energy level, the only sublevel we have is S. If n equals 2, we can have an S sublevel and a P sublevel. If n equals 3, we can have 0, 1, or 2, so the third energy level adds a D sublevel. And then from 4 all the way up to 7, they will have an F sublevel. So again, you can only have certain numbers of, or certain sublevels in certain energy levels, and as long as the number for the sublevel is less than the number for the principal energy level, you're good to go. All right, some other information that you'll need about these. Each one of these has a certain number of orbitals. And remember, an orbital is a location where you can find electrons. And so for the S sublevel, it has 1 orbital. P has 3 orbitals, D has 5, and F has 7. Notice that it increases by 2 every time. And we can use this to say how many electrons each one can hold, which will be very handy for us when we do electron configurations later, excuse me. But one orbital, each orbital can hold 2 electrons. So if S has 1 orbital, it can hold 2 electrons. P has 3, so it can hold 6. D can hold 10, and F can hold 14 electrons. Now, to add a level of complication to this, I had you think right at the beginning of sublevels as being, you're dividing up this band of the energy level, and S is closest, P is next closest, D is next closest. It actually doesn't look like that at all. Each one of these has a characteristic shape. So the S sublevel is shaped like a sphere. The B sublevel is kind of hard to describe other than drawing a picture, but we'll say it's shaped like barbells. And for D and F, it's complicated. We're not even going to deal with trying to think of the shapes. All I want you to know is that they do have distinctive shapes, and they are quite complicated. So for instance, if we are looking at the first energy level, n equals 1, only has the S sublevel, and so it just looks like a sphere. For n equals 2, we now have an S and a P, so what that looks like, the S is shaped like a sphere, and then here we go with the P sublevel. Each one of these 3 orbitals takes a shape kind of like this with the nucleus in the center. So that's actually one orbital that exists on both sides of the nucleus, and then there's another one at 90 degrees to that, and then another one at 90 degrees to that, which means coming into and out of the paper. And so each one of these lobes off of there is part of a P orbital and then the S orbital, and then as it gets more complicated, you add the D and the F orbital as odd shapes surrounding this. So the shape of an atom is actually fairly complicated. All right, that's our sublevel. Remember, that's basically breaking down different locations closer to or farther from the nucleus. They do have their own shapes, and they have certain orbitals. The next number that we're going to deal with is actually the one that tells us which orbital we're looking at. So this number tells us which orbital we're concerned with, and this is pretty arbitrary in that these numbers can really take whatever value you want. It really doesn't matter so long as we keep track of what we filled all of them with. And so the values for this one will range from -3 to +3. And maybe I should say to +3 so as to avoid any confusion. And the way it works is this. We still have our 4 sublevels, right? We have S, P, D, and F. And what we're going to look at is the fact that we need to have names for each one of these orbitals. Now in the S orbital, or the S sublevel rather, we just have one orbital. And so we name that orbital 0. So to give an example, suppose we're looking in the 3rd energy level, so n equals 3, and we're looking at the S sublevel, so n equals 3, L equals 0. The orbital that would be in would be 0. There's no choice. There's just one orbital there. For P, we have 3 orbitals, so we need 3 names for our P orbitals. So we call them -1, 0, and 1. And again, these are just names for the orbitals. We could call them George, Ted, and Bob if you wanted to, but these are the numbers that we've assigned as names to them. So each one of these 3 orbitals has a name, 0, -1, and +1. And it really doesn't matter which is which or what you call it, so long as you just pick one to assign to it. So which one you use is not a big deal. You can pick any one. These are just names for these 3 orbitals. For D, we have 5, so the names we use are -2, -1, 0, 1, and 2. And then for F, we need unique identifiers for each one, and so that looks like this. So depending on what sublevel you're in, these are your options for which orbital it's in. And remember, it's completely arbitrary. You can pick whatever one you'd like. And our last one is our spin number. The Pauli exclusion principle tells us that no 2 electrons can have the exact same quantum numbers. So again, the Pauli exclusion principle, which you will need to know, no 2 electrons can have the exact same quantum numbers. Now look at this. Let's suppose we're in the 1st energy level, n equals 1. The only sublevel we have is L equals 0, and our only orbital for that would be orbital 0. So far, that orbital can hold 2 electrons, and they both have exactly the same set of quantum numbers, 1, 0, and 0. So there must be something going on with spin that will distinguish them. And the way it works is this, is electrons have a quality about them that we call angular momentum, and even though they're not, we can think of it as if the electrons are spinning on their axis, kind of like a top. So you can imagine the electrons spinning that way. Some of them will spin that direction, others will spin the other direction. So some are clockwise, some are counterclockwise. We assign each one of those a number, and it's pretty arbitrary. There's not like you have to know if it's clockwise or counterclockwise or anything like that. We just call one of them +1/2 and the other -1/2. And electrons will not occupy the same orbital unless they have opposite spin numbers, which is where the Pauli exclusion principle comes in. So remember, 4 numbers, 1 for spin, 1 for what orbital it's in, 1 for the sublevel, and 1 for the energy level. And that allows us to completely identify the location of any electron in an atom.